So let me show you an example of use of pseudorandomness in uh, a mathematical experiment. So this has to do with um, counting carries in various sums, but I'm going to use a tool which comes from another part of the book, namely the inversion part, in which we talked quickly about it, but the point is that if we have an interval, uh, potentially a big interval, then we look for the smallest fraction in that interval. What I mean by the smallest fraction is the fraction that has the smallest possible denominator. So this is implemented by essentially taking the endpoints of the intervals, doing the Euclidean algorithm, so we compute the continued fraction, and then we sort of stop um, when they differ. And then the point where they differ, you can compute then the smallest fraction living inside the given interval. So this is something that is fairly efficient, and it's implemented by this code, which is essentially the Euclidean algorithm, and then an the point is then that you sort of go until the two values differ, and then you use the smallest of these numbers that you encounter plus 1 in your um, continued fraction. But let's not worry so much about how it works. Let me show you an example. So if I give it the interval from 0.9 to 1.1, it will of course give me 1. If I give it in the interval from 0.7 to 0.8, I get 3/4, 0.66 to 0.67, I get 2/3, and so on. So it's an exercise to implement this compute carry function that I'm going to use, so I'm not going to show you that. But let me explain what this problem is about by showing you an example directly from the book. So here I have some 8-digit numbers, 3 of them, and I add them up. And I'm interested not in the sum, but in the distribution of the carries that we see upstairs here. So the point is that when I add these 3 numbers, I get 4, and there's no carry. I add these 3 numbers, I get 5, there's no carry. I add these 3 numbers, I get 5, there's no carry. I get At these 3 numbers, I get 18, so I get 8 and a carry of 1. And again, I get 20, I get 0 with a carry of 2, and so on. So I'm interested in what, if I add a number of fairly long numbers, what is the approximate distribution of the various carries. So you see that here um, I get 5 zeros, and I get 1, 2, and 2 ones. So this little program called compute carry, it will look at some numbers and then compute how many carries I get of the different types: 5 zeros, 2 ones, and 1 2. And it's fairly easy to see that the number of numbers that you get uh, in your addition, this gives you a max of the carries that you can encounter. Um, in fact, it's 1 more than the number of carries that you can encounter. So I'm interested in what is the distribution. This is actually something that's been realized fairly recently by work of Diaconis. Um, and so I wrote this little program here, which essentially the thing that it does, it simply simulates this setup. So I generate some random numbers using string tools random. So string tools will create a string with some uh, symbols in it, randomly chosen from a list of symbols or letters, if you like, and the letters that I give them are the digits from 0 to 9. Then I compute a number of these numbers, I compute the carries, and then I just keep track of how many carries I get of each kind. And I also keep, so this is what's done down here, and I also keep track of the square of these numbers because I want to estimate the variance of the observations that I have here, so I can give you a confidence interval. Right, so this is standard descriptive statistics. I have some observations, and based on the observations, I can not only estimate the average, but also say something about how wide the interval is around the average with the standard probabilistic interpretation of what we do with a confidence interval. So I set this up, and now let me show you how it works, and also show you a bit of a problem. So what I've done here is that I've asked Maple to do 50,000 experiments of this kind. I'm taking two numbers each with 10 digits and counting the number of times I get 0 carries and the number of times I get 1 carries. And you see you get these confidence intervals that are disjoint. So this tells me that it's not statistically probable that this is a one-to-one distribution. But on the other hand, you look at these numbers and you sort of say, well, they look awfully close to a half. So it seems reasonable to expect that actually these numbers should have been 50-50. Excuse me. And this, of course, requires an explanation. And in fact, I can come up with a very good explanation just looking over here, because the way that I'm setting up things, um, I'm actually counting the non-carry that's over here. And also, in the beginning, the probability that you're getting a 0 in the second setup is slightly smaller than it is further down the road, because of course down the road you might have gotten a carry, or several, which lifts the sum. So there's something fishy going on in the beginning of this contribution of this computation, sorry, and I don't really know how to solve it, but I can minimize it by sort of saying, okay, I will add, say, numbers with 100 digits, and then I'll disregard what happens at the first 10 digits or something like that. So the idea being that this has to sort of swing in a little bit to become what we're after, and we have to wait for that. So I've changed the program a little bit, so now it will take roughly the same time as before, because I'm doing 500,000 additions. But now the difference is now I have 5,000 numbers, each of 100 digits, and I'm disregarding the first 10. And you see now that I've made this little change. These are two intervals that both contain a half. So when I apply best fraction to them, I get a half and a half, which probably is something we can believe. So of course, this is not so interesting if I only have two numbers that I'm adding. I'm more interested in the case where we have several numbers and we get hence several possible carries. So let me continue this experiment, but where I add up more numbers, not just two, but 3 and more. So it's the same as before. I'm estimating these numbers by a simulation, and I'm running best fraction on it. And the first time I get a sixth, 2/3, and a sixth, and so on. Next time they're all 1/24, 1/24, 11/24, and then the same again. And now as I go on, things are beginning to be a little bit fishy, because of course this is supposed to be a distribution of probabilities, and you'll check that as soon as we come down here, these numbers do not add up to 1. Right, so what's going on here, of course, is that the intervals, I mean the distributions that I estimated gave me these little intervals, and in those intervals, best fraction is looking for a number which has the smallest denominator as possible, and hence there's no guarantee that these numbers will add up to 1. But still, you sort of see something fairly useful here. You see that, first of all, there's some sort of symmetry. Of course, the symmetry is not completely clear, because, for instance, I have here 1/690, 1/648, but probably this is just explained by the fact that Maple finds the smallest fraction, I mean the fraction, I should say the biggest fraction, 1/n, where n is as small as possible, in this interval that the confidence interval that was found by these descriptive statistical methods. And so probably that's just a matter of the size of that interval. So I'm willing to believe that these two numbers at the very ends were supposed to be the same. And as we go further to the middle, it looks as though it is symmetric. So there's various kinds of things that we could do now to speed this up. For instance, it seems like we should probably focus only on the one half and look only at that. So we could perhaps save some time there if we were being clever. But on the other hand, I think I'm ready to start making some qualified guesses of what is going on here. So from now on, I will, in order to save time, I'll show you something that I've prepared. I've doubled the number of experiments here, and it takes a little longer. But you can see it's roughly the same, and we're still waiting for this one here. No. Okay, this says it goes to 7, but it actually goes to 8. So, but you can see I still get fairly consistently the first entries, but already here there's 11 over 20, that's the same, and then I have 8 over 37 and 5 over 23. It's not so clear what I should believe here. And as I go further down, it degenerates somewhat into something that is a little bit hard to explain. So, but what, after staring at this perhaps a little bit, we can start thinking perhaps that the numbers that we encounter at the very beginning, remember they started with a half, then a sixth, then 1 over 24, then 1 over 118 or 117. It's a tempting idea that this is perhaps supposed to be 120, which is the factorial of 3. Then a little bit more of a stretch, I would have to believe that this was 6 factorial, which is 720, so there's some distance there, and so on. But after looking at this a little while and thinking, okay, this is something with probability, probably it has something, it's reasonable that it has something to do with factorial, I made this experiment here. And it's the same experiment as before, but I stopped using the best fraction. What I'm saying is simply, okay, let's assume that this it's a number that has the form integer over n factorial. Then in order to find that integer, I will multiply by n factorial. This is what I'm doing down here. So I'm just taking the average of the confidence interval, which is the best guess of what the number should be. Then I'm rounding off to the closest integer. I'm doing this by adding a half and rounding down. So that's what's going on here. And I get these numbers 1, 4, 1, 1, 11, 11, 1. We've seen this with the correct fractions. And then I have 1, 26, 66, 26, 1. This is now symmetric, which is good. And so that should somehow convince us that the numbers that we're seeing here are in fact supposed to be 1 over 120, 26 over 120, and so on. And we can somehow, of course, this helps my computation because I'm helping Maple to say, okay, this is supposed to be an integer over 120 over n factorial. But you can see already down here I'm getting problems because this is clearly not symmetric. But actually, it turns out that if we go to the OEIS and try to look up these numbers, and this of course is some sort of array, so I'll just naively try to plug it in as 1, 4, 1, 1, 11, 11, 11, 1, 1, what's the 6? Oh, getting help here. 26. Stop here. And then actually there's a hit. It's the triangle of the Eulerian numbers, Euler's numbers, and they somehow have a nice combinatorial description, so it seems very likely that this is the thing that comes up. So that in fact is also a true statement. This is proved by Diakonis and co-author.